event that triggers computation. And so that could be a message arriving, or it could be more fundamentally a task creation, an engineering of deep doing, or a message locking event, or a thread awakening. There's lots of things you can simply trigger your computation. Essentially, the amount of work per trigger is roughly your grain size. And so here's our rule of thumb, is that really you want to get your grain size down to be fairly small. Smaller than a logical think is a good idea for having big vectorizable blocks. Because it turns out you don't actually need the vectorizable blocks to be of the immense maximum memory spanning size. It works better actually if they're smaller because you get more locality. And so you basically want to make them as small as possible, as long as you emphasize the overhead within any vectorization qualifications you may have for that particular architecture. Well, generally, if we say that the average grain size is K, or K is some constant, and V is your overhead, you could arbitrarily choose 10 as, say, a good amount of granularity over the overhead. But K is something you're going to have to adjust based on your problem and on the environment in which you're working. Certainly, no single grain should be allowed to be too large, because again, if you have one grain whose size vastly outweighs the others, then that you won't be able to essentially balance the load against that. So here we have this approximation that the grain size should be smaller than T divided by P, where P is the number of processors. And you can actually express it without P by simply choosing a multiplier, which is just a sort of how many of these you're going to make. And the other thing is that you don't have to have the optimal grain size, and you can achieve something which is close to optimal without actually considering the number of processors as a factor. So here, we have several slides and we're moving to a use case. And this is one of the application codes that we work on all the time. This is the NB code. So this is a classical Newtonian formulation that we use to study the motion of atoms in finite systems. And specifically, it's in Newtonian mechanics, and we're basically worried about the charge forces operating between particles, and we will evolve those over time so that we can observe the motion of these molecules. There's a time step calculating the forces, and the forces have a few different types that we have different formulations for. For bonding forces, we have a special way of calculating those depending on the type of bond. For the non-bonding forces, we have two different types that are related to our formulation. There's the short distance, which is within a cutoff that is actually defined by the constructor of the system, but is typically on the order of 10 angstroms. And then long distance, which is given a different formulation, because within the short distance cutoff, you're computing your force with every particle in the short distance. And so that's going to be n squared. And if you did that with every particle in the system, you'd be n squared across the entire size of the system, which would give you a fairly terrible scaling problem. So long distance is computed using a different algorithm to make the problem more achievable and roughly than long n. And we also use multiple time stepping, which allows us to compute the long range force less frequently than every time step. So how does this give us a breakdown of granularity? Here, we're going to move to the decomposition scheme because the choices you make in decomposition are going to directly affect the rest of your program. And so there will be some choices that limit you and some choices which give you degrees of freedom optimization. In this case, with Randy, we're looking at a hybrid decomposition where these blue boxes represent decomposing the space of the molecules into what we call patches. Usually these patches will contain a chunk of the molecule. And then the force interaction between these patches is represented by these computes, these interaction points, where the interaction between any two of these patches is handled at the compute, and the computes can then be handled and migrated independently of the patch decomposition. So in this case, for this decomposition, you have 14 patches. So one of the problems that came up as we were studying Mandy was this Grainsize performance problem. And here is a histochromatic view of the Grainsize of each of these computes. And we can look at this and say, well, it's bimodal for one thing. And that actually represents the problem in that we have this reasonably large number of objects that have this sort of reasonably smaller grain size, and then you have this other distribution of objects that have a much larger grain size. And as soon as you scale out further and further in a strong scaling paradigm, you're going to have this point where the amount of work per processor begins to approach the granularity of the individual large objects, and you will not be able to achieve load balance by moving them, because that will be the essentially largest work unit. And so to solve this, we want to split these compute objects so that we have more objects, and we will incur some overhead for doing this because we have actually split these and they now operate as individual parallel units. But by having more work units, you're able to achieve a better balance, which will allow you to get better performance. If we look at the distribution here, you can say that for the basic decomposition, where we just have this patch grid, we end up with the sort of this breakdown over here of the force evaluation. If we actually split them, so we would call it two-way X, we're splitting along one dimension, cutting the patches in two, and then we end up with a different distribution, which works better. As we move into how to operate in the charm load balancing framework, we're going to talk about a few of the different options that you have. And so here, the strategies are more or less categorized by how often they operate and how frequently they operate in terms of when you're going to trigger them. And this is essentially a choice that you have at the application level in terms of how you want to interoperate with the load balancing framework. And the choice that you make will be influenced by how your application runs. And so we can look at doing it just at the start. And so after you basically lay things out, you can simply do one load balancing. That will be an option. And if your program doesn't really have dynamic imbalance, then that would probably be fine. In the current scheme of computers, where the machine itself will continue to operate in roughly a regular rate, as you go to the future, if the machine itself is varying itself over time due to heat constraints, then you'll actually have dynamic load balance inflicted upon you, and you'll have to cope with that. After the initial one, you could choose a periodic solution, and this is actually sort of the typical state-of-the-art approach for most applications. What they do is they find a period of time in an application in which it is sort of natural to trigger a new load balancing phase. And it could be that you programmatically, with application information, know that you're undergoing a significant change, and so you should rebalance after that. Or it may be that you still have a certain period, some large number of time steps is enough to develop some imbalance, after which point you should rebalance. The third approach is continuously, and this would be the case where you have an extremely dynamic imbalance, and so you can literally be migrating objects all the time. There are use cases for this, but it's currently fairly rare for applications to choose to do this. The other thing to consider is where the decision is to be made, and this depends a lot on the kind of problem that you're solving and how big the environment is in which you're solving the problem. If you look at a sort of standard default scheme, it's going to be fully centralized. Because if you collect all the load information in one place, you can then make the most fully informed decision about the load. However, if you collect all the information in one place, you have created a resource bottleneck. And you've created a sequential point of decision making. And so the time required to make that decision could be too long. You could also make a completely distributed choice, where essentially you simply consult the neighbors in the node processor space to look to see who has more load than you are, and have that load migrated to you, for example. And that's how the neighbor scheme would work. So in this case, you typically have a fairly nice constant in terms of load relationship. You communicate with a finite number of neighbors with whom you exchange load information. And the decision itself is completely distributed, and so there is not a single point that becomes a bottleneck. That's like this is, of course, you only know about locality. And so if there's some global problem, it will take you a very long time for that global imbalance to diffuse. So if you look at some use cases, in a typical particle situation, it ends up being dynamic load imbalance introduced because of the problem space itself. The particles themselves are moving throughout the actual simulated space, and therefore, with this rigid decomposition, you will have clumps where that will become larger, and other spaces that will become more diffuse and have less load. And so, even if you had a perfect load to begin with, because you have priority to do that, over time, you will not. And of course, you may be starting with a highly non-uniform distribution to begin with, as is the case in cosmology, where you're typically studying space, where most of it is empty, but large chunks of it that you care about are also completely non-uniform distribution. So those balancing is a huge challenge. These situations also occur in material science, and there are other approaches that use structured grids, because essentially the areas of interest can evolve over time, and then you're studying something like crack propagation. You're not interested that much in the force computation far from the crack, because there's not much going on there. And so you tend to have ever finer grids at the wavefront, which will move with the wavefront. And so resolving that efficiently over time will require dynamic load balancing. Similar situations in unstructured grids. So if you look at one of the ways that we approach load balancing, part of our approach is leveraging our runtime system. And so we're using measurement-based load balancing. And we can do that because the runtime system has awareness of the objects and the communication. And so we can actually measure the load of any compute object, and we can consider its communication partners, and we can use these decisions to help with load balancing, rather than having to instrument that yourself when you're in the application. One of the key here is that in most scientific codes, they display what we call the principle of persistence, and that is that the load now will be a very good predictor of the load in the next time step, modulo radical changes. Even if dynamic behavior is occurring, as in the case of particle systems, in most cases, the particles are not moving that fast relative to the time step. And so the amount of load imbalance that occurs at any one point is relatively small. And so any prediction based on what has happened is often fairly good. How this works is we record and we observe the performance, and we collect that information into the database, and then we can trigger decisions based on the observed load. And if you look at one of the classical approaches to using this is essentially how Mandy uses a load balancer. We have some regular number of time steps, which are just running without instrumentation, and then we decide to turn on instrumentation. And the reason why we don't keep it on all the time is that, like any other kind of measurement, it introduces overhead. And so you don't want to have that on all the time when you simply want to compute as fast as you can. But you want to observe under some conditions so that you can get a sense of where you need to rebalance. And so we'll turn on instrumentation for some number of time steps to get a sense of where the load is. Then we will trigger a detailed, we call aggressive, or from scratch load balancing, at which point we would base our decision not based on where things currently are in terms of each object per processor map, but based on a new idealized mapping based on the load that we have just measured. And we'll finish that motivation, and we'll take some more measurements after that to see how well that decision worked. And in this case, we'll trigger a refinement, and a refinement balancer will take the current positioning as key and just try to make small adjustments by minimally moving within the set object processor map. And then you move on with normal time stepping, and then at subsequent points, periodically, or triggered by awareness of load problems, you might trigger further refinement steps to keep up with the evolving nature of your system. So this is a snapshot of the load balancing strategies available in Chart++. There's actually more of these kind of being added fairly regularly. And so if we look at the scheme here, we essentially have the from scratch strategies of the greedy load balancer and the greedy load balancer that uses the communication grid. And a variety of other ways of dividing up the scheme. And so you could look at recursive bisection, you could use the METIS library for repartition your load graph. There's network topology aware centralized load balancer. There's the refined load balancer. There's a refined load balancer that considers the communication graph. There's ways to combine them. In point of fact, you can actually use more than one of these to make a decision. ORB. And then we look at the neighborhood strategies. So if you wanted to not use a centralized scheme, you could use the completely distributed scheme of the neighborhood load balancer and then the communication version. And finally, we have the hybrid option, which allows us to combine strategies. And so this can minimize some of the challenges that you encounter with centralized load balancing, but still give you an effective decision which leverages the existing load balancers. So, to consider one of the use cases that we've encountered in the past, we could look at this crash propagation problem, and here we're looking at the number of iterations per second here versus the iteration number. You see that we begin with a pretty good rate. And then here we have these load balancing steps where we're just periodically triggering load without any awareness of the application's properties. So this would require really no application intervention to trigger this kind of thing. But here in this iteration, we suddenly experience this tremendous decrease in utilization. The number of iterations per second drops hugely. And this happens essentially because of the simulation itself is undergoing a phase change between elasticity and plasticity at the wavefront. So some of the objects have suddenly had a huge change in computational load as they undergo this change. And so now, some of our objects are taking a lot of time that previously took the same time as everything else. So we introduce this load balance problem on the application itself. And then when we do a load balancer, we can move objects around to rebalance the load based on the now observed behavior and return to a pretty good utilization, but it's still a little slower because we're actually doing more work. That's one of the interesting properties of that kind of code. So, completely distributed load balancing, you can actually use centralized strategies out pretty far. You can do the terascale centralized strategy will more or less work all right. It's as you move up into trying to get to serious petascale territory that centralized load balancers run out of the scheme and encounter the limitations which require other corrections. And so a few other things come into play at that point, and we have load balancers that can help cope with these. So here, there's these two extremes where you could use purely centralized load balancing, that works fine for a small regime, or you could use fully distributed load balancing in the case of a very large processor grid. And in fact, distributed also, because it's fairly, because it's essentially a small regular workload, also helps as a way to cope with frequent imbalance. So if you need continuous rebalancing, distributed balancers and neighborhood balancers are one of the good approaches under this solution. The other thing that comes up on these large machines is the cost of communication varies tremendously between any two processors. And so if you look at BlueGene architectures and Cray architectures of today, they are these torus architectures, where the cost of communicating across to a node that is many hops away in the torus is actually multiplied by the number of hops. And so here, we're going to be aware of the topology when we do placement and load balancing so that we don't migrate two high-degree communicators away from each other and thereby significantly increase the computational cost in overhead of their communication. Similarly, you also have to deal with the information problem. Because you have more processors, you have a larger load balancing problem. And the problem is always for the number of processors times the number of objects. So the more of those you have, the bigger the problem is, and the problem itself can become too large to solve on any one processor. And in fact, even trying to accumulate the information from one processor may overload the communication system and may simply overload the network. So now, we need to have a way to operate on less information at any one point. So there are schemes for that that are fairly well established. And there's also ways to combine these things. And so, if you look at one of the things that we're working on recently is trying to deal with the fact that both of these schemes have this these limitations. One, you have these bottlenecks in centralized. Two, in a completely distributed strategy, you don't have enough information at any one point to make an ideal decision, and possibly not even to make a reasonably optimal decision, due to the fact that you're only aware of local minimum and local maximum in a distributed case. So we can actually combine these and get essentially a way to address these two situations. So here, we're looking at overheads. Just to give you a visual demonstration of essentially the problem that happens with centralized load balancing. Here, we have memory usage, and then here we have the number of objects. So it's fairly reasonable with 128,000 objects. But as we go up to 1 million objects, you can see that the memory usage is now peaking over the space footprint that you have per core of BlueGene architecture. So you wouldn't actually be able to use a centralized load balancer for 1 million objects on larger BlueGene machines. There simply is not enough space to do centralized load balancing. Not only is it not enough to still have memory for your computation, there is simply not enough. So the problem becomes untenable unless you do something different. That's where the hierarchical, or also sometimes called hybrid bias for different reasons, load balancers come into play. So here, what we can do is we can partition the processor set rather than having completely global versus completely distributed. We can set up these regions that should be chosen naturally as a processor group, and then apply different strategies at each level of our decomposition choice across the processor space. So here, if you look at the bottommost level, this is the finest degree. Here we divided up our objects. Sadly, the labeling is not as clear here as it could be. But the idea here is to have between 0 and 1K, and then we have these sort of 1K block choices of objects, and we can take a balancing choice within those regions, and then we can pass up information about the region to the level above, and to the level above that, and then when a balance is found, an imbalance is found between this region and the next region, we can exchange a token and have those regions exchange work. And so at the very top, you can use a simple refinement scheme because you don't want to make aggressive changes across these large groups. And at the bottom, you can be using a much more detailed scheme. And as refinement finds that there's an imbalance from this region to the next region, it can tell the overloaded region to give some work to the less loaded region. And at the bottom, you can use a centralized scheme. In this case, we're talking about using a simple greedy scheme. And so here, within each of these regions, you can have the optimality of a centralized scheme and across them the lower information requirements of a refinement-based scheme. And really this will have moved the token and exchange the amount of work between these two regions. So look at the performance of this. We can see that the greedy column LB changes its total memory footprint substantially from the traditional way to the newer hierarchical way. And so now we actually get the memory. Furthermore, the actual time to make a decision, the quality of the decision on the right is essentially unchanged. Mechanically, we're going to take a little shift here in transition to how one actually introduces load balancing into electronic applications. And so, in order for this to work, we need to be able to not only have you define the granularity carefully, but in your char objects, you need to know how to move them. So first, to know how to move them, you need to know how to serialize them, to pack them, and unpack them from here to there. And that is what the PUP framework is for. So here we're going to describe pupping in the lower still mechanical sense, to just review it, to give richer information about it than we've done in the manual. So the idea here is a char typically starts here at the user constructor, which could be, there's an alternate way of constructing it would be through the PUP. So if it's being migrated, then there's the migration constructor, which comes from the PUP inject. So if you are arriving, the object is being moved into a place, then the popper object is going to be in the unpacking state. And then you can make choices based on that. In your code, you will see that. But here we're going to let them on a char, usually has your constructed. User methods are executable. At any time, a popper could be called used to add to basically determine the size of the object. And at any time, something might decide to migrate you. And I mean by any time would be in the base case where you have decided to use anytime migration. And so this is essentially something that could be called at you at any time in the anytime migration sense. You as the application user have control of that choice. So it doesn't necessarily happen to have your object in flight at any time. You can influence the frequency with which this happens. And then at the end of your object's life, you will call the instructor in a little bit way. So if you look at the important things to the popper, the key would be if you're being migrated out, then this call will be instantiated. And so if you wanted to know to do something specific to your object at the point when it's about to be migrated, this call will be inheritable and you can override it. You can do something special. Furthermore, the states that matter are the PUP decided, packing, unpacking, also the constructor, and migration in, there's the migration constructor, the unpacking constructor, and then the stat of CK just migrated. So again, when you have just arrived, you can make a choice to do something particular. And choices that people would often make would be that there are cases where there may be an application level construct which keeps track of, say, which objects are on the same processor. And so you might, for example, if you're about to migrate, unregister yourself from your application level construct, and when you are being migrated in, you will now register yourself with that application level construct. Another important subtlety here is that the size that your object reports during the size of the state should be the same as the size that you would report for packing and for unpacking. Otherwise, you will have a memory error. So look at the actual process of packing. Look at the char object here, and in this case, this is sort of standard in the complexity level that we expect for a char object, in that it's got a bunch of local variables. Some of them are just member variables. One of them is a pointer to heap. This is kind of typical of how codes are arranged. You have a bunch of sort of state variables, which have various quantities that are important to your application, and then you've got some dynamic chunk of memory that is actually containing a column or something data step. And so if we're going to move that object, we need to make sure we can do all that consistently. And so we're going to be serializing that down into this serialized data. And so what we're going to do is we're going to walk through these memory variables, lay them out, and in this case, for standard primitives, there's a nice, you can simply say pop this primitive, and it will do the right thing. For your heap data, there are pop constructors which will handle fairly primitive like arrays of different objects. So if you want to pop an array of this, that's important for you. You can call it pop array, and that'll handle that. For more complicated uses of heap memory, you are going to have to do something in your code, which we'll see in a moment. You'll have an if conditional inside of your pop method. So if unpacking, for example, you will allocate the heap data, heap space that you need, and then you will populate that in a way specific to your use of that heap. So you're moving like a tree, lots of lay tree out. And as time goes by, we continue to add new functionality to PUP to improve the number of data types that are supported. I guess sort of an average complicated PUP. So this is not designed to be some artificially simple case or artificially complicated case. This is, for a typical char which does a decent amount of the actual engineering work of your application. It's going to look a lot like this. And popping it will have this level of complexity. And so, in this case, we have a bunch of member variables, and we have this dynamic heap pointer, the size of the heap, and then we've got a few more of these pointers that are doing various things that you need to worry about, and we have some methods. So there's your constructor, there's your migration constructor, and you have a destructor. So on the pop side, here, this is the method that you're going to be overriding to actually do the special things for your class. First thing, you want to pop your parent so that you get the traits of inheriting from a char. Then, for simple types, you can just do the p pipe your variable, and pop will do the right thing. Whenever a pop sizer is called, will do the right thing. Whenever unpack, pack. In any of these cases, it will know the correct way to serialize these simple primitive member variables. For the simple local array, you can just pop the type and the size, and it will give you a local copy in the stack. For the heap, you have to do something a little bit different. Before we're going to operate on that, we're going to want to make sure we get the size, so we can do the right thing. And here we have an is unpacking conditional block. So if you're unpacking, you need to allocate memory. Because you have not bet on that processor before. There is no memory there for your heap use. And then after that, we can pop to that pointer the size. Here, we have these other pointers that we have. We can test to see during popping, is it pointing to something? And if it is, then we are going to operate on it to fix it. So we pass along this conditional of whether or not that pointer was null or not. And if it's not null, then you can just set that pointer to be a new thing, local to where you are. And finally, oh, sorry, yeah, I mean to make it the new pointer for my class. There. And set that correct. That basically, as gruesome as it looks, is more or less what is necessary to correctly serialize and unserialize a pop which has a reasonable amount of state, including uses of the stack. And the challenge here, there is a software engineering cost. Right? Every time that you modify that object, in addition to handling changes to the class and its constructor, you also have to go and update changes in the buffer scheme, or it will be packed and unpacked directly at migration time. So here, a couple of these notes. So it's on the heap. Make sure that you get the data off the heap. And you do it recursively. Always remember to make sure that you allocate your data before you unpack into it. It's kind of obvious, but people overlook this. Sizing, packing, unpacking should be the same program order of operations like memory variables. And there's a nice, well, reasonably nice way to test whether or not your pop is valid. And that is to test your balancer using the rotate LB. Now, rotate LB literally just migrates your objects to the n+1 processor. And so it won't actually change your balance. But if your buffer is wrong, the odds of a set fault become extremely large, and because everybody will be moved. And this is useful as opposed to like a regular load balancer, and the regular load balancer will actually usually not move that many objects, depending on how balanced your program is. Whereas rotate LB will move extra. So if you have difficult to reproduce load balancing problems, and you think it might be due to one of your puppers, just throw in the rotate LB, and they will be revealed.
How to pop a tree?
What?
How to pop a tree?
Pop a tree, you pop it recursively. And so for the tree object, you'll have a popper, and then you can move through the tree and pop the children at each recursive call.
And how to maintain the parent-child relationship? Because the parent may have a pointer to the child. How to maintain the relationship?
Right. And so you will recursively you'll go all the way down to the leaves, and you'll be returning up the stack until you can return at each point. To give the new pointer value of the newly constructed node. Using a load balancer is actually pretty simple. You link it using the minus module and instead you name at link time. If you want to use every LD, that's one of the options. if you link with every LD, then at runtime, you can essentially choose from the long collection of existing strategies at runtime. But you have all those linked in if you know that you will only have interest in a few. So you could explicitly link only the strategies that you care about. And then at runtime, you set the balancer. Do that. And then you can actually chain these together to have different balancers called at different periods. So if we look at a pretty simple code example, if we have a code relaxation, then this goes through C. And so in this case, this is an example of what we consider basically the sustained approach, which is using a periodic load balancer, which uses this @sync protocol. And so here, there's this decision that you've made is that if this is a load balancing step, in this case it satisfies that test. And that's the periodicity in which you want to do load balancing for this particular problem. We call that sync. And that basically will be a barrier. And so you'll say we are now synchronized. Otherwise, you're going to resume from sync. And that's one of the methods of the charge. And so you're typically going to put in your own code at resume from sync to do the right thing to resume your application's computation. So in this case, here we're just making a callback to, in this case, the idea here being that there's a main functor called step check-in, which basically has everyone who's been migrated, check in with a single place, and you're just going to contribute to this reduction. And everyone arrives at the root from sync, they're going to contribute to this reduction, and it will give us the max diff, and the callback root will end up being that function on main, which will be called when everyone has contributed inside their resume from sync. And now your main loop will say, oh, once resumed, let's kick off the next iteration. So before we run the fault tolerance, are there any questions about load balancing? All right. So the key here is that once we've defined a way for your objects to be migrated using thought, we now know exactly how to serialize them. And so we can serialize them to persistent storage. Simple way here is that we can just check them all to disk, and you can trigger that using this call, CK start checkpoint, with the CD. And so in this case, this callback is after completion. And so after you're done with your checkpoint, we're going to give that callback and say, checkpoint is now complete. And if we are resuming from that checkpoint, we will also call that same callback. So just have one callback which resumes computation after your checkpoint. And so this can actually be done from the command line, where when you've taken this checkpoint, you'll have written your checkpoint out into a log directory. So on the command line, you can say plus restart and give it the log directory from which you want to restart, and resume from that checkpoint. You can also do in-memory checkpointing using the built-in double memory checkpointing routines. And in this case, you would be resuming from a memory checkpoint after you've experienced a fault. So you've lost one of your processors in one of them. And you've also enable the message logging scheme. And in that case, only the faulty processor will have to be rolled back to a checkpoint, and everyone else won't need to roll all the way back to a checkpoint. But it's not the default scheme but it can be accessed by applications which need it. Important differences between these schemes would be that the message logging scheme is designed to handle more than one simultaneous. So here's the usage for this. Here we have this pretty simple main char, and it's got one read only, which is basically just the pointer to the proxy. But we have to go in and deal with that when we are with the main. And so in this case, we have this next, where if it's one of these steps in which we're going to do a checkpoint, we set up the callback, we call it start checkpoint, and otherwise you do normal work. So, in summary, we are experiencing performance problems, and at first, it looks as though the problem is due to the cost of synchronization. In point of fact, the cost of synchronization is probably a little bit of balance cost, if it appears to be far, far, far greater than the cost that simulation can run the cost based on its overhead. So you should look for a load balance. Okay, well, objects are not very difficult to use, and the load balancing framework is actually fairly user-friendly. So you can try a number of benchmarks that we have to study scaling. This is actually, there was a hands-on tutorial that somebody did. So it's the actual example. I can't provide it if you wish to look at it, but it was actually in one of the hidden slides that we didn't go into. Any questions?
Can two tracks share some data? Then when you migrate my track, then you pump share the data.
They can, but we will need to handle the ordering problem in that just only one of them can really have the data which is going to become the target of the migration, depending on how you want it to work. So if you have charts that share data, and they're going to be migrating together, then for that to work consistently, one of them should be clearly secondary to the other. So one of them should be the owner, and the other the user of that data. And then the owner of the data should migrate and keep data with it, and the consumer of the data should reestablish its connection to that local data after migration. And the way to do that would be using the CK local API. And so you would call CK local using the target char of the owner of the data that you want to have pointed to after you have migrated.
And how to get a good locality? If the two chars access same data or not shared data, if you migrate a chart, then they will not share data. I mean, if a child gets remote data, another child on the same processor may benefit the already fixed data. Migrate that, how to get this locality benefit.
So there are a few approaches to that, depending on how to decompose your problem. One of which is that you could keep data in a construct called the node group. And so in a char node group, there will be one object of that type per for charm mode, which would be for process address space. So chars that are within that node can get a local pointer to the data held by the node using a CK-local call on that node element. So when you're within that same address space, you can use that local pointer. And if you are migrated, you should get a CK-local pointer to the node group on that node, on the place you have migrated to. And that way, those chars that need to share that data within the address space will have only one copy that they need to work on if it's read-only, for example, or wrote, or infrequently, when that works very well. If they are modifying that data on the fly, you'll have to worry about synchronization and consistency. And you can actually have them operate using methods on the node group, and you can trigger those methods to be exclusive, so that only one exclusive method on that object can be wiped in one time. And that will give you sequential consistency for those exclusive calls.
Another question is, can you use multi-threading multi-thread in a node?
I can understand that.
Multi-thread, multiple thread, just stable process.
Yes. So one of the things that we didn't discuss here is that Charm has a user-level threading model, and there's a few different ways that it can be interfaced with. The usual scheme would be to use what we call our SMT machine layer. And so what that would typically do would be it would create one pthread per core, and you would have one of those pthreads be dedicated to communication and the rest to be worker threads. And so that's one of the ways to exploit thread-level parallelism. Another is that you can use the actual Charm threaded entry method API. And in that case, you can use the threaded model for operations on Charm.